Okay, so
the definition of argument then if it has inverse, then it identifies so
yeah. Last time we defined, I guess, we did direct sums, but so you asked about isomorphism.
yes.
So an isomorphism met between two vector spaces. Omega W over in the linear map, it says what we mean by inverse is this, right? A head composition B head is just identity of W, and B head composition A head is the identity of, okay? It is not clear from this definition that if A is an isomorphism, then the inverse is also a linear map, right? It's not clear, but we can see that. I mean, so if although it is not clear from this definition, we have the inverse yani like we say an inverse, but inverse is just a function satisfying these two conditions. But from this definition, it is not, obvious that if it is linear, its inverse is also linear. But it's easy to see. So let's see the proof. Proof of we have this also linear. Well, first of all, both A head and B head are 1 and 2, right? Okay, now A head composition B head is identity of W, means what? Implies that for any W, I have identity of W. W. So, and this implies that. This implies that. So, identity of W is of course W. So, a head of W is just W. This means what? So this is true for any W in W. So this means that any W is in the image of A head, right? Inside A head, you put something and you get W. Therefore, W is in the range. So this means that A head is on. Okay, A head is also. Efendim?
Niye bütün tablolar içinde olan? Yani niye hepsi aynı?
Çünkü bu identity nedir ya? Identity'nin içine koyarsanız o çıkıyor. So this means that first of all, A head is onto, right? Okay. Similarly, okay. And D head is injected. How can we see this? If D head of W1 is equal to D head of W2, then we get what? And suppose that these are all equal to D or some D, then of course we have the following. A head of B head of W1, right? What is this? This is just A head of B, because B head of W1 is equal to A head of B. But this implies that also A head of B head of W2. Yes, but on the other hand, A head composition B head of W is equal to W. Therefore, this is also equal to W1, and this is also equal to W2. Right? Because A head composition B head is identical. Therefore, if I apply A head B head to W2, I will get W2. But this is the same thing as A head B head W1. Therefore, this will also equal to W1. This means what? This means that so if B head of W1 is equal to B head of W2, then W1 is equal to W2. This means what? This means that B head is 1 to 1, right? Hence, B head is 1 to 1. So, this relation gave me two things. This relation, this composition, identity gave me two things. A head is onto, B head is 1 to 1. But I have also the other way around relation. Similarly, we have this B head composition A head is identity of B. And this will give me which properties? So that this will give me. So if this is identity, this one is onto, this one is injected. If I have this, then this will tell me that this one is onto, so that we have the onto and A head is 1 to 1. So as a result, we see what? We have an isomorphism A with the inverse B head. Then both A head and B head are 1 to 1 and onto, both of them. Tamam mı?
In some books, it's given that isomorphism is the there is a bijection thing that you can say that these statements are equivalent.
Yeah, I mean, bijection means 1 to 1 and onto them, right?
converse laws of
Yeah,
there's a bias, then it takes.
yeah. So if I have an isomorphism with inverse B, then both of them are actually bijections. They are both 1 and over. What we claim is a little bit more. We also claim that B hat is also linear. Now let's see why B hat is linear. Well, let's look at this one. So, to show that B hat is linear, I have to prove two things. First, B hat respects addition and respects scalar multiplication. Let's start with the first one. Let W1, W2 in W. Then let's look at this expression. A hat of B hat W1 plus W2 minus B hat of W1 minus B hat of W2. Okay. What is this equal to? Well, A hat is a linear map. I have three vectors. This vector minus this vector minus this vector. Since A hat is linear, we should have this. This is equal to A hat of B hat of W1 plus W2 minus A hat of B hat of W1 minus A hat of B hat of W2. But what is this gadget? This is A hat of B hat of something. But the composition is identity, therefore, this is just W1 plus W2 minus A hat of B hat of B1, W1. So this is W1 minus A hat of B hat of W2. This is just W2. So the result is just 0. Okay. So what we have seen is that A hat of this expression is equal to 0. But A hat is 1 to 1, right? And A hat of 0 is already 0. So both 0 is mapped to 0 and this element is mapped to 0. Therefore, this element and 0 must be the same. So since A hat is 1 to 1, we see that whatever you put inside A hat, which is in this case this expression, B hat of W1 plus W2 minus B hat of W1 minus B hat of W2 is equal to 0. But this is equal to 0 means what? That's equal to 0. Hence B hat of W1 plus W2 is equal to B hat of W1 plus B hat of W2. So that's the first condition for B to be a linear map. Yes.
Yeah.
Aha, evet.
Zaten Siyo'nun
Aha.
yani burada bantuman olduğunu göstermek gerek var mı?
Tabii ki var. Zero map'i düşün, her şeyi sıfıra götürüyor. Zero'yu zero'ya götürüyor. Birebir mi oluyor?
Ama mesela burada birebir olduğunu yazmamıza gerek var mı? Yani
Var. Yani bunu bak. Bu elemanın sıfır olduğunu nasıl söyledim? Dedim ki A hat 2 tane elemanı sıfıra götürüyor. Ama bu birebirse sıfıra giden tek bir eleman kullanıyor. Dolayısıyla bu iki farklı görünen şey aslında aynı. Dolayısıyla bu eleman sıfıra eşit olur. Tamam mı? Sorusu olan var mı? So this is the first condition for B to be a linear map. What is the second condition? Similarly, A hat of B hat lambda W minus lambda E hat W is equal to what? Well, again, A hat is linear, therefore this is just A hat of B hat of lambda W minus A hat of lambda times B hat of W. Well, again, since they are inverse of each other, this is just lambda times B. And what about this one? Well, first of all, A hat is linear. Therefore, I can take this constant outside. So this is just lambda times A hat of B hat of W. But then, again, since they are inverse of each other, this composition is just identity. So we get 0. So what we see is then again, this expression is mapped to 0, but since A hat is linear, there is only one element which is mapped to 0, that is the 0 element. So again, this element B hat, B hat of lambda B minus lambda B hat of W must be 0. But this implies that B hat of lambda B is just lambda W is just W times B hat of lambda times B hat of W. So B hat satisfies this condition and this condition. Therefore, B hat is linear. Tamam mı? Yes.
Do we know the things in the branch domain and the domain of data?
Sure, I mean, a hat is defined on the whole B.
But for example, in this, we had W1 plus W2 minus something.
By assumption, a hat is defined from W, and from the definition of being invertible, there is an inverse, and inverse is defined on the whole W with values in B. Therefore, anything in the image of this is in the domain of A hat. Tamam mı? Tanımdan geliyor. Yok, yanlış yaptım. Sorusu olan var mı başka? Okay. Again, last time we defined so-called direct sum, right? So let's WD basis over SEO K to K. And consider the direct sum. Then this gadget has two subspaces which are isomorphic to W and D. Namely, we may consider the following. Okay, the subsets, this one, B comma 0. Remember, these are just pairs of vectors, right? Suppose I choose the second component, the 0 element of this vector space, then this is a subset of this. And this one, this time I choose the zero vector of V, but choose arbitrary vector from W, subsets of V direct sum W are indeed subspaces of V direct sum W. And actually, these subspaces are isomorphic to B and W, right? Note that. These subspaces are isomorphic to W and V and W respectively. What is that? How can we write an isomorphism from these subspaces into V and W? Well, to make notation simpler, let's give a name to these. Let's call this V0, okay? And this one, let's say W0. These are subspaces. I will leave this as an exercise to you. Why these are subspaces? You know, this gadget and this gadget are subspaces of this. You have to prove two things, right? If you take two elements from this set, then their sum is in the set, and scalar multiples are also in this set. And it is clear, of course, if you take V1 times 0, V2 times 0, if you add them up, you will get V1 plus V2 times 0. It has the same form. And if you multiply this by a lambda scalar, then you will get lambda times V, comma, lambda times 0, but lambda times 0 is already 0. So you get again an element in the same subset. Therefore, these are subspaces. We claim that these subspaces are actually isomorphic to V and W, and I guess it is clear. So let's write down an isomorphism. Actually, I shouldn't say an isomorphism. Of course, there are many isomorphisms, but there is a canonical one. I will explain what does this mean. Canonical isomorphism. Canonical isomorphism from V to V0 is as follows. Canonical bir isomorphism yazacağım. Hep yönünde ya da eylem içinde I B. Can you tell me an isomorphism? So you should tell me the image of any vector. What should be the image of this be? It will be an element here, and it should be an isomorphism. So what should be the image of P?
Minus B to
Minus
E to the
Y minus B. Okay. Well, canonical one is this, right? Take B to B comma 0. This map is clearly 1-to-1 and onto because its image is this. Any element of this form is in the image of that map, and it is clear that if you choose different elements here, you will get different pairs here, right? Clearly, ID is 1 to 1 and it's 1 to. What is the image? And it is linear, right? It is linear. It is also linear. Göstermeme gerek var mı? Should I prove that it's linear? Göster derseniz yapacağım. Ama yok, gerek yok artık. Öğrendiklerini diyorsanız yapmayacağım. Sınavda sorarım. Lineer olması. One to one. Onu da mı gösteriyor? Korkutmayın ya. Lineer için ne gerekiyor? İki şey değil mi? Toplamı koruyacak, skalar multiplication koruyacak. Yani lineer uzay olmanın şartlarını koruyacak. O yüzden ona lineer diyoruz. So, we have to prove two things. D1 plus D2. This should be IV D1 plus IV D2. But what is the image of this? This is the definition of the map. It sends an element to V, 0. So this is map to D1 plus D2, 0. Now I am in this space. The direction below. What is the addition operation here? Addition operation is just component-wise addition, right? This element can be written as D1, 0 plus D2, 0, right? If you add this two, you just get this because D1 plus D2 is this, 0 plus 0 is this element. But what is this? It is just IV of D1 and this is IV of D2. Okay, so first condition is satisfied, right? This map respects vector addition. What about scalar multiplication? Similarly, IV of lambda D. What is this? Well, by definition of this map, this is just this. But 0 is just, of course, you can write it as lambda times 0, so that we can take lambda outside. Right? Lambda times d, 0 is just lambda d, lambda 0, which is 0. So it is this element. And what is this? This is just IV of. So IV respects scalar multiplication. Therefore, IV is 0. Oldu mu? Anlaşıldı mı? Anlamadıysanız bu sorun var. Anladınız ama ne gerek vardı diye düşünüyorsanız. Hani yazdığım şeyler gerekli. Anlamış olabilirsiniz ama gereksiz buluyorsanız da o zaman bir şeyleri kaçırıyorsunuz demektir. Tamam mı? Var mı sorusu olan? Yani bunu niye yaptık, burası anlaşılmadı diye düşünüyorsanız sorun. Anything you don't understand about this? What is the inverse of that map? Can you tell me the inverse? So here IE goes from V to V0. It is 1-to-1 and onto, therefore it has an inverse map. Let's call it JD from where to where? From D0 to D. It should be the inverse of this map. Can you tell me how it is defined? So it should be defined on an element of this type, right? So its image should be what? Just B, right? And we can check that this is also 1-to-1 and 2, or just check that compositions are identical maps. And once you okay, let me write that. No change. ID composition JD is identity map of B0 and JD composition ID is just identity map of B, so that ID and JD are isomorphic. And they are both 1-to-1 onto, and they are both linear maps. Okay. Birinin lineer olduğunu biliyorsak diğeri otomatikman lineer. Değil mi? Onu gösterdik. If one of them is linear, the other one is automatically linear since they are inverse of each other. Tamam mı? So this means what? This means the following. Our vector space, similarly, of course, similarly, W is isomorphic to what? To W0. Why not? The map. Buradaki metni ne olacak? I, W, nereden? W'dan W0'ya. Nasıl? W olacak? 0, W. Right? It will send it to the second component. Okay. One important thing about this direct sum is the following. Note that any element V comma W of V plus W in the as a sum of elements from V0 and W0 in a unit way. Yani şu V comma W ben nasıl yazarım? I claim it can be written as a sum of two elements, one element from this, the other element from this in a unique way. Of course, in this case, it is easy, right? Because V0 is just the set of elements V comma 0 and W0 are the elements 0 comma W. I can write this, of course, as follows: 0 comma this, V comma 0 and 0 comma W. This is V0 and this is in W0. And this is unique, right? Çünkü yani burada V olduğuna göre ve W0'da burada 0 olduğuna göre V komponenti bu D olmalı. Değil mi? Burası da 0 olmalı. Burada da W olduğuna göre burada W. In this example, of course, it is clear that any element can be written like this in a little way, but that's actually a defining equation of this direct sum. Also note that there are again canonical reductions from V0 and W0. What are they? Bir tane projection yazabiliriz. Buna P head of V V0. Nasıl? İkili aldığım zaman V kama W'yi nereye göndereceğim? It should be mapped to an element of this type. But of course, this is the map. And V comma W is mapped to 0 comma W. These are projections. What we mean by a projection is that their squares are identical, right? Projection neydi? Linear map olacak. So a projection is a linear map whose squares itself, not identical. I'm sorry. Okay. Here. Also, what is this map? So, square of this map applied to an element. So this is PV0. PV0 of this is what? It is just V comma 0. And what is the int of this? Well, you keep this component the same and send the second component to 0. Well, it is already 0. So it is this. But what is this? It is just PV0 of the comma W. Right? And this is true for all V comma W with the direct sum W. So what we see is that this composition is the same as this map at all the elements of our vector space. Right? I have two functions which takes the same value at all elements of its domain, right? Where it is defined. Therefore, hence V0 had composition V0 has to just V0. So that in other words, is linear, is a privilege. Tamam mı? Bir de şu kanonik lafını kullanıyorum. Onun ne kullandığımı da söyleyeyim. When you say something is canonical, it means that it is defined naturally. You don't need an extra tool to define it. You don't need to make a choice to define it. It is something naturally defined. In case of linear algebra, a canonical linear map means that to define that map, you don't have to choose a basis or anything. It is defined naturally. Okay? So, let me write canonical map. Algebra means that you don't need to see the basis to define. Okay. Examples. A canonical map from a vector space to itself. Just identity map sends everything to right. So identity map from B to D, which sends D to D, is a canonical map. Is a canonical isomorphism. Non-canonical map. We know the following. If you have a linear map from a vector space to itself, then given a basis, you can represent that linear map by a matrix, right? So, if A hat is a linear map from a vector space to itself, and if you are given a basis, let's say, basis of n elements, let's say, basis for D, then to this map, we can associate a matrix, right? A, I, J, and n by n matrix. So we may think of this as follows. I have a map from the set of linear transformations or operators to matrices, right? You give me a linear map, I give you a matrix, which represents this operator in this basis. You see, to define this matrix, I use this basis heavily, right? I write every vector in this basis and then look at its image, write the image in that basis and so on. If I change this basis,
I will obtain another matrix, not the same matrix. Therefore, this association, for example, which is actually also a linear map, is not canonical, right? There is no canonic way of associating a matrix to a linear map, right? If you give me a linear map, what is the matrix for that? You have to give me a basis so that I can write down a matrix representation. Otherwise, you cannot do that. Tamam mı? Yani şu non-kanonik işlem hangisi? Bir lineer map verildiğinde o lineer map'i matris gösterimini bulma işi kanonik değil. Neden? Çünkü bu matrisi bulmak için bir tane baza ihtiyacım var. Hangi baz? Milyon tane baz var. Her baz bana başka bir matris verecek. Dolayısıyla lineer map'lerden matrislere giden kanonik bir map'im yok. Tamam mı? Eğer olsaydı hani lineer map verildiği zaman işte bunun matris gösterimi budur. Onu yapabilmek için kanonik bir tane baz gerekirdi ama kanonik baz da yok. Baz var ama bir sürü var. Birinin diğerine üstünlüğü yok. Right? Something is not canonical means there are many actually objects that corresponds to a given object, and none of them has a none of them is superior with respect to the other one. Okay, like basis of a vector space. I mean, you have millions of bases, and each one gives you a matrix representation. That's why matrix representation of a linear transformation is not a canonical procedure. Tamam mı? Okay, so let's stop in the second hour. I'll start use space.